The universe is built on a lie. Everything we can see and touch, every star and planet and galaxy, is just a fraction of reality. The rest is hidden in the dark. Two cosmic phantoms, dark matter and dark energy, together form 95% of all existence, yet they slip through our detectors and bend light with invisible hands. By the end of this journey, you will understand the 30 greatest mysteries that define our cosmos. We will explore the ghostly scaffold that holds galaxies together and the repulsive force tearing space itself apart. What is the true nature of the cosmos we call home? Our story begins not with a flash of light, but with a glaring inconsistency. In the quiet of a Swiss observatory, an astronomer named Zwicky was studying a distant swarm of galaxies known as the Coma Cluster. He measured how fast these island universes were whirling around their common center, and the numbers he found were impossible. According to the laws of gravity, the galaxies were moving far too quickly. At those speeds, the combined gravitational pull of all the stars and gas he could see should have been utterly insufficient. The cluster should have flown apart long ago, its members scattered into the lonely void. Yet there it was, holding together. Zwicky concluded that something unseen must be providing the extra gravity, a hidden mass binding the cluster. He called it dunkel materie, dark matter. For decades, his idea was largely ignored, considered a curious anomaly. Then, in the 1970s, astronomer Vera Rubin turned her telescope closer to home, studying the serene spiral arms of our neighboring galaxies. She expected to find what textbooks predicted. Stars at the edges of a galaxy, far from its bright core, should orbit more slowly, just as Pluto trudges around our sun compared to the swift Mercury. But her meticulous observations revealed something astonishing. Stars on the outer fringes were orbiting just as fast as those near the center. It was as if the entire galaxy, from its brilliant heart to its dim outskirts, was embedded within an enormous, invisible sphere of mass, a ghostly halo providing a gravitational grip where none could be seen. Rubin's work transformed a fringe idea into an undeniable truth. The universe is filled with a substance that does not emit, absorb, or reflect light. It is the invisible architect of the cosmos. This dark matter forms a vast, intricate scaffold upon which the luminous universe is built. Without it, galaxies would never have clumped together in the early universe, and the majestic spirals and ellipticals we see today would simply not exist. It is the hidden framework, the cosmic skeleton, and here lies the heart of the first great mystery. We have mapped its gravitational shadow across the sky. We have measured its overwhelming dominance. It outnumbers normal matter by a factor of 5 to 1, but we have no idea what it is. It is not made of atoms. It is not planets, black holes, or cold gas. It is something entirely new, a fundamental particle that has so far eluded every detector ever built on Earth. We are surrounded by the architecture of an unknown builder, living in a universe whose primary ingredient remains a complete enigma. The hunt for this invisible architect became a race to define a ghost. If dark matter is not made of atoms, what could it possibly be? Scientists have proposed several compelling candidates, each a different flavor of cosmic phantom. For decades, the leading suspect was known as a WIMP, a weakly interacting massive particle. Imagine a particle far heavier than a proton, yet so aloof it barely notices the existence of ordinary matter. It would stream through you, through the entire Earth, without a single collision. This aloofness is its defining trait. WIMP were the perfect theoretical fit for a long time. They emerged naturally from popular extensions to the standard model of particle physics, and their predicted abundance from the Big Bang matched the amount of dark matter we observe in the cosmos almost perfectly. It was an elegant solution, and enormous, sensitive experiments were built deep underground to catch one. Laboratories nestled in old mines or beneath mountains use vast vats of ultra-pure liquid. waiting for the unimaginably rare moment a WIMP might bump into an atomic nucleus and create a telltale flash of light or a tiny charge. But so far, the detectors have remained silent. The great WIMP hunt has turned up empty, forcing physicists to broaden their search. This brings us to a very different idea: the action. If a WIMP is a heavyweight ghost, an action is an ethereal whisper. It is predicted to be billions of times lighter than an electron, a wisp of a particle born not from dark matter theory, but from a puzzle within the strong nuclear force that binds atomic nuclei. Actions would behave less like discrete particles and more like a pervasive, rippling cosmic field. In vast numbers, they could collectively exert the gravitational influence we see. Because they are so incredibly light, they would exhibit strange, wave-like properties on astronomical scales. The search for actions is just as ingenious, using powerful magnetic fields to try and convert them into detectable microwave photons. Then there is the sterile neutrino, a hypothetical sibling to the known neutrinos that flood the universe. Unlike its interactive family, a sterile neutrino would, as its name implies, interact only through gravity, making it another perfect dark matter candidate. But what if the answer is not a new particle at all? Early on, astronomers considered massive astrophysical compact halo objects. These are ordinary but dark objects made of atoms, like rogue planets, neutron stars, or primordial black holes formed in the chaos of the early universe. They would hide in the halos of galaxies, unseen but gravitating. However, extensive surveys using a technique called gravitational microlensing, where these objects would briefly magnify the light of a background star as they passed in front, have shown that MACHO cannot account for more than a tiny fraction of the dark matter needed. They are a piece of the puzzle, but not the solution. So the search continues, a global detective story played out in particle colliders that recreate Big Bang conditions, in silent underground chambers, and in precision telescopes scanning the sky. We are trying to catch a shadow by the sound of its footsteps, building traps for a substance that may be fundamentally, heartbreakingly shy. The silence of our detectors is itself a profound message, telling us the truth may be stranger than any WIMP or action we have yet dreamed of. This silent framework was not just a passive bystander, it was the master sculptor of the cosmos. In the beginning, moments after the Big Bang, the universe was a near-perfect soup of particles and energy, smooth to an almost unimaginable degree. But within that smoothness, imprinted by quantum ripples from the first instant of time, were tiny, random patches where the density of dark matter was ever so slightly higher. Think of a vast, calm ocean with gentle, nearly imperceptible swells. These swells were the dark matter seeds. Because dark matter feels gravity but not the pushing pressure of light, it could begin to clump together under its own weight long before normal matter could. Ordinary atoms, in contrast, were caught in a furious battle. They were buffeted by intense radiation pressure, a blinding light that prevented them from settling down. The dark matter, invisible and immune to this light, quietly collapsed into a colossal cosmic web, a network of filaments and knots stretching across the expanding universe. This web became the gravitational foundation for everything we see. The slight overdensities acted as traps. As the universe expanded and cooled, the radiation pressure eased, and ordinary matter, primarily hydrogen and helium gas, finally felt the steady, deep pull of these dark matter wells. It flowed along the filaments, pooling at the intersections, drawn into the growing gravitational pits. There, the gas could compress, heat up, and eventually ignite into the first stars, lighting up the dark matter halos and birthing the very first galaxies. This narrative is not just a theory. It is tested by some of the most complex computer simulations ever run, like the famous Millennium simulation. Scientists program the laws of physics and the initial conditions of the early universe, set dark matter in motion, and let the virtual cosmos evolve for billions of years. The result is breathtaking. The simulation produces a large-scale cosmic web with clusters and voids and filaments that matches the observed distribution of galaxies in our own universe with stunning accuracy. It is a powerful validation that dark matter is the essential ingredient for building the universe as we know it. Yet, here lies the paradox. When we zoom in on the fine details, the simulation and reality begin to disagree. The simulations predict that dark matter halos should have a very specific density profile, a sharp, steep peak of density at their very centers, a cusp. But observations of the motions of stars and gas within dwarf galaxies suggest their dark matter cores are more like a gentle, constant density plateau. This is the core cusp problem. Furthermore, the simulations predict that our own Milky Way should be surrounded by thousands of small, dark satellite galaxies, the leftover crumbs from its formation. Our telescopes, however, have only found a few dozen. This is the missing satellites problem. It is as if the blueprint for the universe is perfect on the grandest scales, but the instructions for building the individual rooms are slightly off. These mismatches are not failures, they are clues. They could mean dark matter has properties we have not yet accounted for, perhaps a way to interact with itself or with normal matter just a tiny bit, smoothing out those central cusps and suppressing the formation of the smallest galaxies. Or they could point to something equally profound about the nature of gravity itself. The very success of the dark matter model has illuminated its most puzzling imperfections, showing us where the next great discovery might be hiding. But this invisible scaffold faced its ultimate courtroom test in a spectacular cosmic collision far away. The evidence comes from a system known officially as 1E2657-58, but more famously called the Bullet Cluster. It is the aftermath of a titanic crash between two galaxy clusters, each containing hundreds of galaxies. This event, unfolding over hundreds of millions of years, provided a perfect natural experiment. In such a collision, the different components of the clusters behave in very different ways. The galaxies themselves are mostly empty space, so they pass through one another like swarms of bees, largely unaffected. The vast clouds of hot gas that fill the space between the galaxies, however, are a different story. This gas is normal baryonic matter, and it is so diffuse and tenuous that when the two clusters collide, the gas clouds slam into each other. They create immense friction and pressure, heating up to millions of degrees and glowing brightly in X-ray light. This hot gas gets stuck in the middle of the collision, like two clouds of smoke merging. Astronomers can see this brilliant, tangled knot of gas with X-ray telescopes, but where is the mass? To find it, they used a technique called gravitational lensing. By measuring how the cluster's gravity warps the light from galaxies even farther behind it, they can map the total mass distribution, both seen and unseen. The result was stunning and definitive. The map of total mass did not lie in the middle with the glowing gas. Instead, it had sailed right through the collision site, coinciding almost perfectly with the locations of the galaxies themselves. This proved that the vast majority of the mass in these clusters is not the hot, interacting gas. It is something else, something that felt the pull of gravity but felt no friction, no pressure, and emitted no light. It is dark matter, physically separated from the normal matter by the violence of the crash. This observation is arguably the single most direct and visual proof that dark matter is real, and that it is a distinct, non-interacting substance. For scientists proposing an alternative theory called modified Newtonian dynamics, or MUND, the bullet cluster posed a serious challenge. MUND suggests that we do not need dark matter at all, that instead our understanding of gravity is simply incomplete and behaves differently on the vast scales of galaxies. But MUND struggles profoundly with the bullet cluster. If gravity were just modified, the mass should be where the visible matter is, which is mostly the hot gas in the center. It cannot explain how the gravitational pull could be so clearly divorced from the location of the normal matter. The dark matter interpretation, however, explains it with elegant simplicity. Here, in the wreckage of two universes colliding, we have a fingerprint. It is the signature of the ghost caught in the act of being something entirely separate from everything we know. This cosmic fingerprint is most clearly read through a phenomenon of pure spacetime geometry. Gravitational lensing is the universe's ultimate sleight of hand, a direct consequence of Einstein's revolutionary insight. Mass tells spacetime how to curve, and curved spacetime tells light how to move. A massive object, like a galaxy cluster, acts as a natural lens, warping the fabric of reality around it. When light from a distant background galaxy travels through this warped region on its way to our telescopes, its path is bent. It does not travel in a straight line. From our vantage point, the result is a cosmic mirage. The image of that background galaxy can be stretched into long, faint arcs like smears of celestial paint. It can be duplicated, appearing as multiple, identical copies arranged around the foreground cluster. It can be magnified, bringing impossibly distant objects into view. But this is far more than just a spectacular visual effect. It is a precision tool. By meticulously measuring the exact shapes, positions, and distortions of thousands of these background galaxies, astronomers can perform a kind of cosmic tomography. They can work backwards to map the precise distribution of all the mass in the foreground cluster that caused the lensing, regardless of whether that mass emits light. This is how we see the unseen. The resulting mass maps are breathtaking. They reveal the dark matter halo not as a vague blob, but as an intricate, sculpted structure, often with peaks and subhalos tracing the invisible scaffolding. Some of the most profound examples come from projects like the Hubble Space Telescope's frontier fields. Here, astronomers pointed Hubble at massive galaxy clusters, using them as natural telescopes to peer even deeper into the universe. The images are a labyrinth of light and shadow. Dozens of distant galaxies are stretched into luminous arcs, circling the cluster core in a delicate Einsteinian ring. The mass map derived from this twisted light shows the dark matter distribution in stark relief, a giant, diffuse cloud that cradles the visible galaxies within it. In some cases, the map even reveals dark matter clumps where no galaxies are seen at all, ghostly islands of pure mass adrift in the void. Each arc, each duplicated quasar image, is a data point in an equation, a silent testimony to the gravity of the dark. It allows us to weigh galaxy clusters with incredible accuracy, confirming time and again that the visible matter is merely the decorative trim on a hidden, massive framework. Through this gravitational mirage, we are not just looking at dark matter's shadow, we are tracing its very silhouette against the light of the cosmos. Yet the most compelling evidence for this invisible architecture is not written in the distorted light of distant galaxies, but in the oldest photograph ever taken. It is a snapshot of the infant universe, a faint, cold glow that fills every cubic inch of the sky. This is the cosmic microwave background, the afterglow of the Big Bang itself, released when the universe was only 380,000 years old. At that moment, the hot, dense plasma of particles and light finally cooled enough for atoms to form, allowing photons to travel freely across space for the first time. That light has been traveling for over 13 billion years, stretched and cooled by the expansion of the universe into a microwave whisper just 3 degrees above absolute zero. But it is not perfectly uniform. When we look with exquisitely sensitive instruments like the Wilkinson Microwave Anisotropy Probe and the Planck Space Observatory, we see a tapestry of tiny temperature variations, a mottled pattern of slightly warmer and slightly cooler patches. These fluctuations are the fossilized imprints of sound waves rippling through the primordial plasma, and their pattern is a Rosetta Stone for cosmology. By analyzing the precise size and distribution of these hot and cold spots, scientists can decode the exact recipe of the universe at that early time. The results are breathtakingly precise. The data tells us that ordinary matter, the atoms that make up stars, planets, and us, accounts for only about 5% of the universe's total energy and mass. Dark matter, which was already clumping silently in the background, made up roughly 27%. The remaining 68% was something else entirely, a placeholder we will soon explore. This CMB measurement is why we can state with such confidence that dark matter is not just a galactic fix, but a fundamental, universal ingredient. It was woven into the fabric of reality from the very beginning. These ancient temperature ripples also tell us how much total matter exists and how it is distributed, allowing us to predict the large-scale structure of the universe we see today with uncanny accuracy. This complete picture, where a cosmological constant represented by the Greek letter lambda teams with cold dark matter, forms the backbone of our standard model of cosmology, known as the lambda CDM model. It is the simplest framework that fits virtually every observation we have, from the first light of the CMB to the accelerating expansion we measure today. The CMB is the foundation upon which our entire understanding of the cosmos is built, and etched into its faint light is the undeniable signature of the dark. Deep beneath the Gran Sasso mountain in Italy, shielded from cosmic rays by 1.4 kilometers of solid rock, a quiet detector has been telling a story no one else can hear. For more than 20 years, the Dama Libra experiment has recorded a faint, rhythmic pulse. Its heart is an array of ultra-pure sodium iodide crystals chosen for their sensitivity. The principle is straightforward. If a dark matter particle, known as a WIMP, were to drift through the detector and collide with an atomic nucleus, it would produce a tiny flash of light, a scintillation. The team meticulously records these events, searching for a pattern within the noise, and they claim to have found one. The signal rises and falls with a precise annual cycle, peaking every year around June 2nd and reaching its lowest point around December 2nd. This timing is not random. It is the exact signature you would expect if Earth were sailing through a steady wind of dark matter particles as we orbit the Sun. In June, our planet's orbital motion adds to the solar system's speed through the galaxy's dark matter halo, creating a headwind. In December, we are moving against that flow, creating a relative tailwind. The number of expected particle collisions would subtly increase and decrease with the seasons. Dama Libra insists their data shows exactly this modulation, a whisper from the halo itself. This claim has ignited one of the most heated and enduring debates in modern physics. On one hand, the signal's persistence is extraordinary. A seasonal artifact or an instrumental effect would likely not maintain such a clean, 20-year sinusoidal pattern perfectly in sync with the calendar. It suggests something real is happening in that mountain hall. Yet, here is the profound conflict. Other major experiments designed with different target materials and even greater sensitivity have seen nothing. The Xenon experiment using liquid xenon deep underground, the LUX experiment in South Dakota, and the Panda X experiment in China all have reported null results. They have not seen the seasonal modulation, nor have they detected the steady rate of WIMP collisions that Dama model would imply. It is a stark contradiction. Either Dama Libra is seeing something that these other, arguably more sensitive detectors cannot, or the signal is not dark matter at all. This standoff forces scientists to explore exotic possibilities. Could dark matter be something more complex than the simple WIMP model? Perhaps it interacts only with certain types of nuclei, like the sodium or iodine in Dama crystals, while remaining invisible to the xenon in other detectors. This idea, called the inelastic dark matter model or other non-standard interactions, is actively investigated. Alternatively, the signal might stem from a subtle, seasonal environmental effect within the mountain itself. Changes in groundwater, temperature, or even cosmic ray muon rates that coincidentally mimic the dark matter wind. Every proposed systematic has been scrutinized, and the Dama team maintains they have ruled them all out. the mystery endures precisely because it is so specific and so stubborn. It is a siren song from the dark, a rhythmic beat that could be the first direct touch of the cosmic phantom, or it could be an elaborate cosmic mirage, a lesson in how the universe can fool even our most careful instruments. Until another experiment can independently confirm or definitively refute it, this annual modulation will remain a tantalizing and controversial ghost in the machine. But the grand success of the cosmic web reveals troubling cracks in the foundations. As our telescopes peer into the faintest, smallest galaxies, the elegant predictions of dark matter theory begin to fray at the edges. This is the small-scale crisis, a series of puzzles suggesting that our understanding of the dark architect's handiwork is incomplete. The first glaring mismatch is known as the core cusp problem. Sophisticated computer simulations of how cold dark matter should clump under gravity consistently produce halos with a very specific internal structure. The density of dark matter should spike dramatically toward the very center of a galaxy, creating a sharp, steep peak, a cusp. This makes intuitive sense as gravity pulls everything toward the middle. Yet, when astronomers study the motions of stars and gas within real dwarf galaxies, the smallest and darkest galaxies we know, they find something very different. The dark matter in these galaxies appears to be distributed in a gentle, constant density core, like a soft ball of cotton rather than a sharp needle. The gravitational pull from the center is simply not strong enough to match the cuspy prediction. It is as if something has been stirring the dark matter pot, preventing it from settling into that dense central peak. The second mismatch is called the too big to fail problem, and it is just as puzzling. Our simulations of galaxy formation predict that our Milky Way should be surrounded by hundreds of substantial dark matter halos, massive enough to easily host bright, star-filled satellite dwarf galaxies. Yet we observe only a handful of such faint satellites. The simulated halos are, in essence, too massive and too gravitationally powerful to have failed to form many stars. So where are all the galaxies these halos should contain? They appear to be missing, or they remain utterly dark, devoid of any stars at all. These are not minor accounting errors. They are fundamental discrepancies between what our best theoretical models produce and what we actually see in the sky. So what could be smoothing out those dense cusps and suppressing the formation of galaxies in those massive halos? One leading idea points to the fury of stars themselves. This is the concept of astrophysical feedback. In the early lives of small galaxies, the first generations of massive stars lived fast and died young, exploding as supernovae. These colossal blasts would have injected tremendous energy into the surrounding gas, blowing it out in powerful winds. If the dark matter halo is dynamic and responsive, this sudden removal of normal matter from the galactic center could dramatically alter the gravitational landscape. As the dense ball of gas is expelled, the gravitational well at the center becomes shallower, and the dark matter particles responding to this change might migrate outward, transforming a sharp cusp into a soft core. It is a cosmic game of gravitational seesaw. Another, more radical possibility is that dark matter itself is not completely cold and collisionless. What if dark matter particles can interact with each other, not through the electromagnetic force, but through some new dark force? This is the self-interacting dark matter hypothesis. Imagine a halo of dark matter not as a swarm of ghosts that pass through each other unnoticed, but as a vast crowd where particles can gently bump and nudge one another. These tiny interactions would transfer energy from the densely packed center to the outskirts, smoothing out the sharp cusp into a constant density core over time, much like how stirring a cup of coffee evens out the temperature. This self-interaction could also explain the too big to fail problem by making it harder for small, dense clumps of dark matter to survive, effectively erasing the smallest halos before they can ever light up with stars. The small-scale crisis forces us to ask a profound question. Are we witnessing the complex side effects of normal astrophysics, the messy aftermath of stellar explosions, or are we seeing the first hints of dark matter's true, rich physics? The answer lies in the faintest galaxies, where the dark architect's signature is written most clearly and where our theories face their most stringent test. Perhaps the answer to the small-scale crisis lies not in a new particle, but in the most extreme objects the universe can create. The idea of macho, dark objects made of ordinary matter never fully faded. It has simply evolved into a more exotic and compelling possibility: primordial black holes. These are not the black holes we know, born from the dramatic collapse of massive stars. Primordial black holes are relics of creation itself, hypothesized to have formed in the first chaotic fraction of a second after the Big Bang. Imagine the infant universe as a seething, dense broth. Within it, random quantum fluctuations in density could have been so intense that pockets of space simply pinched off under their own gravity, collapsing directly into black holes of almost any size. They could be as small as an asteroid or as massive as many stars, forged not from dying suns, but from the raw energy of the cosmos' birth. This makes them a uniquely fascinating candidate for dark matter. A vast population of these ancient, invisible holes drifting through galactic halos could collectively provide all the missing gravitational pull we observe. They would be the ultimate macho, perfectly dark and nearly impossible to see. For this to work, however, they must exist within a very specific mass window. If they are too small, say around the mass of a large asteroid, they would have evaporated away by now due to Hawking radiation, a slow quantum leak of energy. If they are too large, their gravitational effects would disrupt star clusters or distort the cosmic microwave background in ways we do not see. The sweet spot seems to lie between the mass of a large planet and about 1,000 times the mass of our Sun. Within that range, they could, in principle, account for all the dark matter. But science thrives on constraints, and the hunt for these phantom holes has been a masterclass in creative detection. One powerful method is gravitational microlensing. If a primordial black hole of, say, stellar mass were to pass directly between us and a distant star, its gravity would act as a tiny lens, briefly magnifying the star's light. Massive, automated sky surveys have watched millions of stars for years, looking for these characteristic brightenings. They have found some intriguing events, but not nearly enough to suggest that planet-sized or star-sized black holes make up the bulk of dark matter. This has ruled out vast swaths of the possible mass spectrum. Observations of the cosmic microwave background provide another critical check. If numerous primordial black holes existed in the early universe, their gravity would subtly alter the pattern of the ancient light, and their voracious absorption of matter would inject extra energy. The pristine agreement between the observed CMB and the standard lambda CDM model places tight limits, particularly on black holes smaller than a large asteroid. Then came a thunderclap from a new kind of astronomy. When the LIGO observatories detected gravitational waves from merging black holes, it sent a shockwave through the cosmology community. The black holes involved were surprisingly heavy, each tens of times the mass of our Sun. Could these be primordial black holes captured in a cosmic dance? It is a tantalizing thought. Their unusual mass does fit within a narrow, still allowed window for dark matter candidates. However, the calculated rate of these mergers, based on the few events we have seen, suggests that such heavy black holes are likely rare. They cannot be the sole constituent of dark matter, or we would see far more gravitational wave signals from their constant collisions. The collective weight of evidence from microlensing, the cosmic microwave background, and gravitational waves has now painted the primordial black hole landscape with remarkable detail. Huge portions of the possible mass range are now empty, ruled out. But like a detective closing off alleyways, this process has left a few intriguing corridors open. There remain narrow, allowable mass bands where a significant fraction of the dark matter could still be hiding in the form of these ancient relics. They are not the simple, universal answer we might have hoped for, but they remain a viable, haunting piece of the puzzle. The universe may be threaded with the silent scars of its own violent birth, black holes that are not dead stars but cosmic fossils from the first moment of time. While primordial black holes retreat into narrow windows of possibility, another ghostly candidate is stepping into the brightest spotlight. The action, born from a flaw in the heart of the atom, has become the dark matter frontrunner for many physicists. Its story begins not with missing gravity, but with a profound symmetry in the laws of nature that should be broken, yet somehow is not. This is the strong CP problem. Inside every atomic nucleus, the strong nuclear force holds protons and neutrons together. The mathematics of this force allow for a certain kind of asymmetry, a parameter that would make the neutron possess a tiny electric dipole moment, a slight internal charge imbalance. If this asymmetry existed, it would violate both charge and parity symmetry, hence CP. Experiments have measured the neutron with exquisite precision, and it is perfectly, mysteriously symmetric. The expected asymmetry is at least 1 billion times smaller than theory predicts. It is as if a fundamental dial in the universe's machinery is tuned to zero for no apparent reason. In the 1970s, physicists Roberto Pexi and Helen Quinn proposed an elegant solution, a new, fundamental field that pervades all of space. This field would automatically adjust, cancelling out that problematic asymmetry and forcing the dial to zero. The quantum ripple of this field would be a new particle, named the Action by Frank Wilczek after a brand of laundry detergent, for its ability to clean up a messy problem. If this particle exists, it would be astonishingly light, potentially billions of times lighter than an electron. But in the vastness of the cosmos, it would be produced in staggering numbers during the Big Bang. These actions would not be fast-moving relics. They would be born cold and slow, collectively behaving like a coherent, rippling field that fills the galaxy. This makes them a perfect candidate for cold dark matter, the very scaffolding we need. Their ghostly nature is extreme. They would interact so weakly with normal matter that they could pass through light years of lead without a bump. But they possess one magical, detectable property. In the presence of a strong magnetic field, an action can, very rarely, convert into a photon, a particle of light. This is the key to the hunt. We cannot catch the action itself, but we can try to coax it to reveal itself as a faint whisper of microwave radiation. This is the mission of experiments like the Action Dark Matter E-experiment, or a DMX. Imagine a high-tech listening post for the cosmos. At its heart is a supercooled metal cavity, a resonant chamber plunged to temperatures near absolute zero to silence the random noise of heat. A powerful superconducting magnet surrounds this cavity. The idea is that if actions are the dark matter flowing through our galaxy, they are streaming through this chamber right now. The strong magnetic field provides the catalyst. If an action's mass corresponds to the precise resonant frequency of the cavity, it can convert into a single microwave photon, which would then resonate and be amplified by exquisitely sensitive quantum sensors. The team does not tune the cavity to just one frequency. They painstakingly scan across millions of possible frequencies, like slowly turning a radio dial across the static of the universe, listening for one perfectly pure, faint tone that signifies an action of a specific mass. For decades, this search was limited by technology. The signals were too faint to detect above the noise, but a revolution in quantum amplification has changed the game. Using devices called superconducting quantum interference devices and even quantum-limited amplifiers that operate on the very edge of Heisenberg's uncertainty principle, a DMX and other experiments like HOYSTC and CAPP are now reaching the sensitivity needed to hear the action song, if it is there. They are listening for a note played by the universe's most pervasive yet silent field, a note that could solve two profound mysteries at once: the pristine symmetry of the neutron and the invisible mass of the cosmos. The silence of the cavity is not empty, it is charged with anticipation as we wait for a ghost to finally sing. But what if the action is just one citizen of an entire hidden nation? The search for dark matter is undergoing a profound shift, from a hunt for a single, elusive particle to the exploration of a complete parallel universe. This is the concept of the dark sector, a whole cosmos of particles and forces that operate entirely under their own rules, interacting with our familiar world of atoms and light only through the faintest, most tenuous whispers. It is a universe within the universe, invisible and all around us, and if it exists, it must have its own forces, its own light, its own rules of engagement. This brings us to one of the most elegant and compelling bridges proposed between our world and the dark photon. In our universe, the forces we experience are carried by messenger particles. The photon, for instance, is the particle of light and the carrier of the electromagnetic force. It is how electrons know to repel each other and how light travels across the cosmos. In the dark sector, there could be analogous force carriers. A dark photon would be the mediator of a dark electromagnetic force, governing how dark matter particles interact with each other. But crucially, this dark photon might not be completely isolated. Through subtle quantum effects, it could have a tiny mixing with our ordinary photon. This mixing would be the cosmic loophole, a way for the two universes to communicate. It would mean that, very rarely, a dark photon could transform into an ordinary photon, and vice versa. This tiny connection could solve multiple puzzles at once. For years, certain particle physics experiments have recorded tantalizing anomalies that stubbornly refuse to fit the standard model. One of the most famous is the measurement of the magnetic moment of the muon, a heavier cousin of the electron. Its measured value shows a slight but persistent deviation from theoretical predictions. Could this be the fingerprint of a dark photon subtly influencing the experiment? Similarly, an experiment at the Hungarian Academy of Sciences several years ago reported an unexpected bump in the data when firing protons at lithium targets, hinting at the decay of a new particle about 34 times heavier than an electron. Some theorists proposed this could be a dark photon, a messenger from the hidden world briefly flashing into existence. The hunt for these phantom particles is now a major frontier. Scientists are looking for them in two primary ways. The first is through precision experiments that look for subtle violations of energy and momentum. If a dark photon is produced and then decays back into ordinary particles, it would leave a very specific signature, a narrow peak in the data at a precise mass. Experiments like those at the Large Hadron Collider and dedicated facilities like Jefferson Lab in the United States are meticulously sifting through collisions, searching for these telltale spikes against a background of known processes. The second method is even more indirect, looking for the effects of dark photons already existing in the cosmos. If dark photons permeate space, they could mediate a new, long-range force between ordinary matter. This would be a fifth force of nature, beyond gravity and the three forces of the standard model. Exquisitely sensitive laboratory experiments are testing the law of gravity at microscopic distances, searching for any deviation that could signal this new interaction. The dark photon conundrum represents a dramatic expansion of the mystery. We are no longer just looking for the missing mass. We are searching for the hidden architects, the laws, and the very fabric of an entire shadow universe that has been evolving alongside our own for 13 billion years. Finding a dark photon would not just identify dark matter, it would open a door to a whole new cosmology, revealing that our reality is merely the visible tip of an unimaginably vast and complex iceberg. The smooth cosmic web and its ghostly scaffolding were not the final word on our universe's fate. For decades, cosmologists had assumed the great story was written in a single, predictable arc. After the explosive birth of the Big Bang, the universe was expanding, yes, but the collective gravity of all the matter within it, both dark and luminous, was constantly pulling back, acting as a cosmic brake. The central question was simply how much matter existed. Would there be enough gravity to eventually halt the expansion and pull everything back in a fiery big crunch, or just enough to slow it forever toward a gradual, frozen halt? Two rival teams set out to measure this deceleration once and for all, using the universe's most reliable mile markers. They focused on a specific kind of stellar explosion, a Type Ia supernova. These occur in binary star systems where a dense white dwarf steals matter from its companion until it reaches a critical, precise mass and detonates in a thermonuclear blast. Because the trigger mass is always the same, the intrinsic brightness of these supernovae is nearly identical. They are standard candles. By measuring how bright such an explosion appears from Earth and knowing its true brightness, astronomers can calculate its exact distance. Furthermore, by analyzing the redshift of its light, how much the expanding universe has stretched its wavelengths, they can determine how fast the universe was expanding when that light was emitted billions of years ago. The two teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, painstakingly searched for these distant beacons. They pointed the world's most powerful telescopes at patches of dark sky, returning night after night to discover the faint, telltale pinpricks of supernova in galaxies billions of light years away. They compiled their data, measuring distances and redshifts with meticulous care. The answer, when it finally emerged, was not just surprising, it was universe-shattering. The distant supernova were fainter than they should have been, much fainter. This could mean only one thing: these stellar explosions were farther away than anyone had predicted. For the universe to have stretched that much in the time since their light was emitted, its expansion could not have been slowing down, it had to have been speeding up. Some mysterious repulsive force counteracting the pull of gravity was pushing galaxies apart at an ever-increasing rate. The universe was not winding down. It was running away. The announcement in 1998 sent a shockwave through the scientific community. This was not a minor adjustment. It overturned a fundamental assumption about cosmic evolution. The two teams shared the 2011 Nobel Prize in Physics for their discovery, which revealed that roughly 68% of the universe's total energy budget is composed of this mysterious antigravity. They named it dark energy. Its existence meant that the fate of the cosmos was no longer a simple tug of war between expansion and gravity. A dominant, repulsive force was now in the driver's seat, accelerating the expansion toward a profoundly cold, dark, and isolated future. In a single stroke, the mystery of the missing mass was joined by an even deeper mystery: the nature of the nothingness that pushes everything apart. This accelerating expansion demanded a name, a mathematical placeholder for the unknown. The leading candidate is a concept with a deeply ironic history: Einstein's cosmological constant. When Albert Einstein was crafting his theory of general relativity, his equations described a dynamic universe, one that should either expand or contract. But the scientific consensus of his time, including his own belief, held that the universe was static and eternal. To force his equations into this mold, Einstein introduced a fudge factor, a term represented by the Greek letter lambda. This cosmological constant represented a repulsive energy inherent to empty space itself, perfectly balanced against gravity's pull to achieve a stationary cosmos. Later, when Edwin Hubble discovered the universe was indeed expanding, Einstein famously called the cosmological constant his greatest blunder and discarded it. Yet, like a ghost from the past, lambda has returned with a vengeance. In our modern equations, it is no longer a fudge factor, but the leading explanation for dark energy. It represents a constant energy density, a property of the vacuum of space itself. Think of empty space not as truly empty, but as a seething quantum foam. According to quantum field theory, virtual particles constantly flicker in and out of existence, borrowing energy from the vacuum for fleeting moments. This activity should endow every cubic centimeter of nothingness with a colossal intrinsic energy, a pressure that would drive the universe apart. This is the cosmological constant, a simple, elegant idea that the vacuum has energy, and that energy is constant, unchanging over time and space. If lambda is the true answer, it means dark energy is a fundamental feature of the cosmos, as immutable as the speed of light. The expansion will continue to accelerate forever, leading to a cold, lonely fate known as the Big Freeze, where galaxies vanish over the cosmic horizon. But this elegant solution comes with a catastrophic problem, often called the worst prediction in the history of physics. When physicists calculate the expected energy of the quantum vacuum, the number they get is absurd. It is roughly 1 followed by 120 zeros times larger than the value we actually observe from the accelerating expansion of the universe. To match observation, the cosmological constant must be fine-tuned to an unimaginable precision of 1 part in 10 to the 120th power. It is like measuring the width of a single atom against the entire observable universe and finding they are the same. This staggering mismatch is the cosmological constant problem. It suggests one of two terrifying possibilities. Either our understanding of quantum vacuum energy is profoundly wrong, or the universe is exquisitely, inexplicably fine-tuned. Is lambda the simple, final answer, a static number woven into the fabric of reality, implying a cosmos balanced on a razor's edge? Or is it merely a placeholder, a crude approximation for something far more dynamic and strange lurking within the vacuum, waiting to be discovered? Yet the cosmological constant is a profoundly lonely answer, a single number etched into the void for all eternity. But what if dark energy is not a constant at all? What if it breathes, evolves, and has a history of its own? This possibility has a name: quintessence. In ancient philosophy, quintessence was the fifth element, the pure and perfect substance of the heavens, beyond earth, air, fire, and water. In modern cosmology, it is the leading challenger to lambda, a dynamic, rolling energy field that fills all of space. Think of it not as a static property of the vacuum, but as a kind of cosmic weather, a pervasive mist whose density and pressure can subtly shift over billions of years. It is akin to the fabled inflaton field that, in the first fraction of a second after the Big Bang, drove a period of hyper-expansion called inflation, stretching the universe from subatomic size to cosmic scales. Quintessence is like a distant, weaker cousin of that primordial force, awakening in the cosmic afternoon to gently push galaxies apart. The key difference from lambda is dynamism. A cosmological constant is just that constant. Its energy density remains the same in every cubic centimeter of space, yesterday, today, and forever. Quintessence, however, is a field that can roll down a gentle slope in its potential energy landscape. As it rolls, its energy density changes. In the early universe, it might have been diluted and subdominant, allowing matter to clump and galaxies to form. Only later, as matter thinned out with expansion, might the quintessence field have reached a configuration where its repulsive pressure became the dominant force, explaining why we see the acceleration starting a few billion years ago. This offers an elegant solution to the cosmic coincidence problem. Why are we living in the brief epoch where dark matter and dark energy have comparable influences? With quintessence, it is not a bizarre coincidence but a phase in a longer, evolving story. Detecting the ghostly signature of this rolling field is the work of the next generation of cosmology. If dark energy is quintessence, its changing strength would leave a fingerprint on the expansion history of the universe. Astronomers would measure a slightly different rate of acceleration at different cosmic times compared to the unwavering push of a pure lambda. Projects like the Dark Energy Spectroscopic Instrument and the future Nancy Grace Roman Space Telescope are designed to map the universe in 3 dimensions and in exquisite detail, tracing the growth of structure and the stretching of space across 10 billion years. They will look for the subtlest of deviations in the data, a gentle curve in the graph of cosmic expansion that whispers of a field in motion. Is the universe's fate written in immutable stone, or is it being written now by an unseen hand slowly turning a dial we have only just begun to sense? The nature of dark energy doesn't just shape our past, it writes our future. It is the author of the universe's final chapter, and the plot hinges entirely on its true, hidden character. If the cosmological constant is the final answer, a static and unchanging vacuum energy, then the cosmic story has a cold, lonely, but definitive ending. This is the big freeze or the heat death of the universe. In this scenario, the accelerated expansion continues forever, relentlessly pushing galaxies apart. Distant island universes will first redshift into invisibility, then vanish entirely as they are pushed beyond our cosmic horizon, their light never able to reach us again. Our local group of galaxies, bound together by gravity, will remain as a single, merged island in an ever-darkening void. Over trillions of years, stars will burn through their fuel and die one by one. Galaxies will fade from brilliant spirals to dark halos of dead stellar remnants, black holes, neutron stars, and cold white dwarfs. Even these remnants will eventually decay through quantum processes over unimaginable timescales. The universe will approach a state of maximum entropy, a uniform, frigid sea of near absolute zero, where no energy can be harnessed, no stars shine, and no new stories begin. It is an eternal, silent stillness, but what if dark energy is not constant? What if it is the dynamic force of quintessence capable of change? If this field were to strengthen over time, its repulsive push would grow ever more powerful. This leads to the most violent finale imaginable, the Big Rip. First, the accelerating expansion would overcome the gravitational glue holding galaxy clusters together. They would be ripped apart, their members flung into the deepening darkness. Then, the force would turn on individual galaxies. The Milky Way would be shredded, stars torn from their orbits and sent flying into nothingness. As the dark energy density becomes overwhelmingly intense, it would attack smaller and smaller structures. Planetary systems would be dismantled. Eventually, in the final moments, the repulsive force would exceed the very forces that hold atoms together. In a final, catastrophic flash, every molecule, every atomic nucleus, every fundamental particle would be torn asunder. The fabric of space-time itself might be ripped apart. The universe would end not with a whimper, but with a catastrophic, fundamental dissolution. There exists a third, more cyclical possibility. What if quintessence weakens over time or even reverses sign? If the repulsive push of dark energy were to fade away, the ancient tug-of-war would shift again. Gravity, the patient architect, would reassert its dominion. The expansion of the universe would slow, halt, and then reverse. Galaxies would begin rushing back toward each other. The cosmos would contract, heating up as it collapses. In a mirror image of the Big Bang, everything would be compressed into an inferno of increasing density and temperature, a big crunch. This fiery collapse could be an absolute end, a singularity of everything. Or, some theories suggest, it could be a cosmic rebirth, a bounce that triggers a new Big Bang and a new universe, perhaps with different physical laws, in an endless cycle of expansion and contraction. Which of these 3 fates, the freeze, the rip, or the crunch, awaits our cosmos? The answer is encoded in the subtle behavior of dark energy across billions of years. By measuring how the expansion rate has changed from the ancient past to the present, we are essentially reading the final sentence of our universe's story. The mystery is whether that sentence ends with a period, an exclamation point, or simply turns the page to a new chapter. This cosmic story has a number, and right now, that number is telling two different tales. At the heart of modern cosmology lies a single critical value, the Hubble constant. It is the universe's current expansion rate, a measure of how fast galaxies are receding from us for every megaparsec of distance. For decades, astronomers have refined their methods, striving to pin down this number with ever greater precision. They have succeeded spectacularly, but with a shocking result. The two most trusted roads to this answer no longer meet. They diverge, pointing to a fundamental crisis called the Hubble tension. The first road uses the local universe as our laboratory. Astronomers build what they call a cosmic distance ladder. The first rung is built with Cepheid variable stars, pulsating giants whose intrinsic brightness is directly tied to the rhythm of their pulsations. By measuring their pulse period from nearby galaxies, we know exactly how bright they truly are. Comparing that to how dim they appear gives us a precise distance to their host galaxy. The next rung uses Type Ia supernova within those same galaxies. Because these stellar explosions are such perfect standard candles, once we have the galaxy's distance from the Cepheids, we can calibrate the supernova's true peak brightness. We then find these same supernovae in galaxies far, far away, measure how dim they look, and calculate those immense distances. Finally, by measuring the redshift of those distant galaxies, we see how much the universe has stretched their light. Combining the distance with the redshift gives us the expansion rate. Teams using the Hubble Space Telescope, painstakingly observing Cepheids and supernova, have arrived at a very specific number. The universe is expanding at about 73 kilometers per second for every megaparsec of distance. This is the local late-time measurement. The second road looks back to the dawn of time, to the cosmic microwave background. The Planck Space Observatory mapped the faint temperature variations in this afterglow with exquisite detail. The size and pattern of these hot and cold spots are a frozen record of the universe's properties when it was only 380,000 years old. Using our incredibly successful standard model of cosmology, lambda-CDM, we can feed this early universe data into supercomputers and run the cosmic film forward 13.8 billion years. The model predicts what the expansion rate should be today. The answer from Planck is clear and confident, about 67 kilometers per second per megaparsec. The problem is stark. 73 does not equal 67. The local measurement and the early universe prediction disagree by a significant and stubborn margin. This is not a small statistical fluke. The uncertainty on each measurement is now so small that the chance this is a simple error is less than 1 in a million. The tension is real, so what does this rift in the data mean? It suggests a crack in our otherwise beautiful model of the cosmos. Perhaps unknown physics was at play in the very early universe, something that altered the sound waves imprinted on the CMB in a way we have not accounted for. Maybe dark energy is not a simple cosmological constant, but something more dynamic. Its strength could have changed over time, evolving in a way that makes the universe's expansion history different than our model assumes. Some have even proposed new types of dark energy or exotic forms of dark matter that interacted differently in the cosmic dawn. Of course, there is always the possibility of a hidden systematic error in one of the measurements, perhaps in our understanding of Cepheid stars or the physics of supernova. But as each team double-checks and reanalyzes their data, the tension only tightens. This disagreement is not a failure of science, it is its most exciting state. It is a signpost pointing toward something new, a clue that our standard model, for all its glory, is incomplete. The Hubble tension is the universe presenting us with a paradox, and the solution will rewrite our understanding of cosmic history. The universe's expansion history is etched not only in the fading light of supernova, but in the very positions of galaxies themselves. To measure the cosmos, we need a ruler that does not stretch with time, a fixed standard etched into the fabric of space. Remarkably, the early universe provided one. They are called baryon acoustic oscillations, and they are the fossilized echoes of sound waves from the cosmic dawn. In that first hot, dense plasma, dark matter had already begun to clump silently, creating gravitational wells. Ordinary matter, a soup of protons, electrons, and photons, was trapped in a fierce tug of war. The gravity of the dark matter pulled the plasma inward, while the intense radiation pressure of the photons pushed it outward. This created a series of pressure waves, like ripples from a stone dropped into a pond, that raced outward through the fiery universe at over half the speed of light. Then, at 380,000 years old, the cosmos cooled enough for atoms to form. The photons, suddenly freed, streamed away as the cosmic microwave background. The ordinary matter, no longer buffeted by that intense radiation, was frozen in place, stranded at the outermost crest of those ripples. Imagine a wave washing up on a beach and then instantly turning to stone, preserving its exact shape. That is what happened on a cosmic scale. Each overdensity of dark matter at the center of a ripple became surrounded by a spherical shell of ordinary matter, precisely 490 million light-years in radius. This distance became the universe's standard ruler. Over billions of years, these frozen waves expanded with the universe, but their scale relative to everything else remained constant. Today, we see their imprint not with our eyes but through statistics. When we map the three-dimensional positions of millions of galaxies, we find a subtle preference for pairs of galaxies to be separated by that specific, vast distance. It is as if the cosmos has a faint, repeating pattern woven into its structure, a whisper of that ancient sound. Massive surveys like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument are designed to detect this whisper. By measuring the scale of this standard ruler at different slices of cosmic time, looking at galaxies both nearby and incredibly far away, astronomers can trace how the expansion of space has stretched that ruler over the eons. This provides a direct, clean measurement of how dark energy has influenced the universe's growth, completely independent of the supernova method. It is a crucial check with very different potential sources of error, offering a powerful way to constrain whether dark energy is a simple constant or something dynamic like quintessence. The BAOs are a silent, statistical symphony, a rhythm set in motion in the first instant and still beating in the arrangement of galaxies, allowing us to measure the invisible hand that guides the cosmos. The cosmic web is not just a structure of light and mass, it is also a map of profound emptiness. Between the great filaments and glittering clusters lie the true titans of space, cosmic voids. These are not small pockets of nothing, but staggering deserts of near-perfect vacuum, some spanning over 300 million light-years across. Within them, you might find only a handful of isolated, lonely galaxies. If our Milky Way resided in the heart of such a void, our night sky would be almost perfectly black, with no nearby galaxies visible to the naked eye. These voids are the inverse image of the dark matter scaffold, the negative space carved out by gravity over billions of years. As matter flowed into the denser filaments and knots, it drained these regions, leaving behind expansive bubbles in the foam of the cosmos. But these bubbles are not static. They too are evolving, and their growth tells a critical story about the forces shaping the universe. In a cosmos dominated only by gravity, voids would expand steadily as their edges are pulled toward the surrounding dense walls. This natural swelling is a key feature of the cosmic structure. However, the discovery of dark energy added a new, repulsive pressure to the entire universe. This antigravity acts as a cosmic antagonist to the void's natural growth. Think of a void as a balloon trying to inflate in a room where the air itself is pushing outward. Dark energy's repulsive effect actually suppresses the expansion of voids. It counteracts the gravitational tug from the surrounding walls, slowing down their growth. This creates a subtle but measurable signature. By mapping thousands of these voids, measuring their shapes, their sizes, and how those sizes have changed over cosmic time, astronomers gain a unique probe into the nature of dark energy itself. A static cosmological constant would imprint one pattern of void growth. A dynamic quintessence field would imprint another. Furthermore, the shapes of voids are exquisitely sensitive to the laws of gravity on the largest scales. In Einstein's general relativity, the geometry of empty space is still curved by the mass at the boundaries. Alternative theories of gravity predict different distortions in the void walls as they evolve. So, by studying the precise geometry of these immense nothings, we are conducting a fundamental test of gravity in the most extreme low-density environments imaginable. The void phenomenon transforms emptiness from a mere absence into one of our most powerful laboratories. We are learning to read the universe not only by where the matter is, but by where it is decisively not, finding in the great cosmic deserts a clear imprint of the dark forces that rule us all. Perhaps the entire dark universe is a grand illusion. What if we are not missing 95% of reality, but are instead misreading the most fundamental force that binds it? This is the radical proposition at the heart of modified gravity. Instead of invoking invisible particles and mysterious energies, these theories suggest our understanding of gravity itself is incomplete, a close approximation that fails on the vast scales of galaxies and beyond. The most famous of these ideas is modified Newtonian dynamics, or MUND. Proposed by physicist Mordechai Milgrom in the early 1980s, it starts from a simple, elegant observation. The need for dark matter only appears when the gravitational acceleration within a galaxy falls below an extremely tiny threshold, about 100 billion times weaker than the gravity we feel on Earth. Milgrom suggested that at these fantastically low accelerations, Newton's law of gravity changes. Instead of the familiar inverse square law, the force transitions to a different form, one that falls off more slowly. This single tweak, this gentle nudge to the rules, can perfectly reproduce the flat rotation curves of spiral galaxies without a single gram of dark matter. The stars on the outskirts orbit faster because in this regime, gravity itself is stronger than Newton predicts. It is a breathtakingly simple fix for the galactic scale problem. But Newtonian gravity is only part of the story. We live in a universe described by Einstein's theory of general relativity. To be a true cosmological alternative, man needed a relativistic upgrade. This led to theories like tensor vector scalar gravity, or TVS. In this framework, gravity is not just the curvature of spacetime by mass. It is a more complex interplay involving additional fields. A vector field that picks out a preferred direction in time and a scalar field that modulates the strength of gravity. These fields interact to produce the MUND behavior at low accelerations while matching general relativity in the strong field regimes of our solar system. Other ideas, like F of R gravity, propose that the Einstein-Hilbert action, the very core of general relativity, needs modification, making gravity's strength dependent on the curvature of space itself. On their home turf, the scale of individual galaxies, these modified gravity theories perform remarkably well. They naturally explain the tight relationship between a galaxy's visible mass and its rotation speed, a correlation that the standard dark matter model must carefully engineer. They can address the core cusp problem by their very design, predicting the soft dark matter cores seen in dwarf galaxies. For their proponents, this elegance is a powerful argument. Why invent an entire unseen universe when a slight adjustment to a known law can do the job? Yet the cosmos is a harsh judge, and modified gravity faces catastrophic failures on larger scales. Its greatest challenge is the bullet cluster. Remember, the collision cleanly separated the hot, interacting gas from the bulk of the mass which sailed through untouched. Modified gravity theories like TVS tie gravity directly to the distribution of visible matter. The mass should be where the gas is. They struggled profoundly to explain how the gravitational lensing map could be completely divorced from the normal matter, a result that dark matter interprets with elegant simplicity. The second, perhaps fatal, blow comes from the cosmic microwave background. The intricate pattern of hot and cold spots in that ancient light is a precise record of how structure formed in the early universe. In the Standard Model, dark matter's early clumping is essential for seeding those oscillations. Modified gravity theories, lacking this invisible scaffolding, produce a CMB pattern that is a poor match to the exquisitely detailed data from the Planck satellite. They cannot easily replicate the observed ratios of dark matter, dark energy, and ordinary matter that the CMB so clearly dictates. While adjustments and more complex versions are continually proposed, they often begin to resemble the dark matter model they sought to replace, adding hidden fields and fine-tuned parameters. For most cosmologists, the evidence from clusters and the early universe is overwhelming. Modified gravity remains an ingenious, fascinating footnote, a testament to human ingenuity in questioning foundations, but one that has so far failed to chart the full map of the cosmos. It stands as a brilliant answer to a question that, it seems, the universe is not asking. The deepest theories of physics whisper that our universe might be living on borrowed time. For decades, string theory has promised a framework to unify all forces, including gravity, into a single elegant description of reality. Within its mathematical possibilities lies a vast collection of consistent potential universes, each with its own laws and constants. This is called the landscape, but surrounding this landscape is a theoretical no-man's land known as the swampland. These are sets of laws and parameters that seem mathematically possible at first glance, but which are fundamentally incompatible with a consistent theory of quantum gravity. They are dead-end universes, theories stuck in the swampland, and here is where the mystery collides with dark energy. One of the most discussed swampland conjectures suggests that a stable, positive cosmological constant, a perfectly constant, unchanging dark energy like Einstein's lambda, is forbidden. It cannot exist in the landscape. According to this idea, the universe simply cannot have a vacuum energy that is both repulsive and eternally fixed. If true, this would mean our leading model for dark energy is mathematically inconsistent with a complete theory of physics. The universe would be telling us that lambda is not the final answer. Instead, the conjecture pushes us firmly toward dynamic dark energy like quintessence, but it goes further, imposing a strict condition. For quintessence to be consistent, the field that drives it must have traversed a significant distance in what theorists call field space over the history of the cosmos. It cannot be stuck in a shallow trough. It must be rolling down a long, gentle slope. This is not just a technical detail. It creates a direct, testable bridge between the abstract world of string theory and our telescopes. If the field has moved a lot, it implies that the strength of dark energy must have changed measurably over billions of years. Our observations should be able to detect that evolution. Projects like the Dark Energy Spectroscopic Instrument are, in a very real sense, conducting an experiment that could confirm or refute a conjecture from string theory. They are looking for the fingerprint of a rolling field. A confirmation would be revolutionary, proving that the deepest theoretical constraints on reality are written in the expansion history of the cosmos. It would force us to abandon the simple cosmological constant and embrace a universe where dark energy is an active, evolving player. The swampland ideas turn the mystery of dark energy from a cosmological puzzle into a fundamental test of our most ambitious theories of everything. We are no longer just asking what the universe is doing, but whether the universe as we model it is even allowed to exist. We are living in a moment of perfect cosmic balance, and that is deeply suspicious. For most of the universe's history, the cosmic budget was dominated by one component at a time. In the fiery, dense youth, radiation ruled. Then, for billions of years, dark matter held sway, its gravity sculpting galaxies. Only recently, cosmically speaking, has dark energy taken the lead, driving the accelerated expansion. The strange part is the timing. Right now, the energy density of dark matter and the energy density of dark energy are not just close, they are of the same order of magnitude. One is roughly 3 times the other. This seems like a trivial detail, but it is a staggering statistical anomaly. These two components behave in completely opposite ways. Dark matter dilutes as the universe expands. As space stretches, the number of dark matter particles in any given volume decreases like dots on an inflating balloon moving farther apart. Its influence weakens over time. Dark energy, if it is a true cosmological constant, is a property of empty space itself. Its density remains constant, unwavering as the universe grows. This creates a profound divergence. In the past, dark matter's density was vastly higher than dark energy's. In the far future, dark energy will be overwhelmingly dominant as dark matter continues to thin out. The window where their densities are comparable is cosmically brief, a fleeting slice of time lasting only a few billion years out of a trillion-year timeline. And we happen to be alive, observing the universe right in the middle of that special window. Why is this the ultimate coincidence, a random roll of the cosmic dice that just happened to land in our favor? That answer feels deeply unsatisfying to the scientific mind. It suggests a fine-tuning so exquisite it borders on the miraculous. This is the cosmic coincidence problem, and it forces us to consider radical possibilities. One explanation ventures into the realm of the multiverse. If our universe is just one of a near-infinite number in a vast multiverse, each with randomly different values for dark matter and dark energy densities, then we should not be surprised to find ourselves in one where the conditions are just right for the formation of galaxies, stars, planets, and ultimately, observers like us. In most universes, dark energy might be so strong that it rips apart any structure before it can form, or so weak that it never becomes relevant. We exist in this one because it is habitable. Our presence selects for this specific, seemingly fine-tuned balance. This is the anthropic principle in its most potent form. Another, perhaps more thrilling, idea is that this is not a coincidence at all. What if dark matter and dark energy are not independent entities but are dynamically linked? Could they be two manifestations of a single underlying substance? Some theoretical models propose an interaction between them, a kind of energy transfer. As dark matter dilutes with expansion, perhaps it decays or converts in some way into dark energy, feeding the repulsive force and keeping their densities in a kind of lockstep for longer than we would expect. This would make our current epoch less of a fleeting accident and more a predictable phase in a connected cosmic dance. The coincidence problem transforms a numerical curiosity into a philosophical frontier. It asks whether our place in cosmic history is a random accident, a logical necessity of observation, or a clue pointing to a deeper, unified dark sector we have yet to understand. This cosmic coincidence is a clue too glaring to ignore. If dark matter and dark energy are not independent but are secretly talking to each other, the entire story of the cosmos changes. This is the daring frontier of interacting dark sector models, where the two great phantoms are not strangers but partners in a hidden dance. The simplest idea is that dark matter might slowly decay into dark energy. Picture a vast reservoir of invisible mass, the dark matter halo of a galaxy, slowly evaporating over billions of years. Its essence is not lost, but transformed into the repulsive energy of the vacuum, feeding the very force that pushes galaxies apart. This creates a direct link between the two dominant components. As the universe expands and dark matter naturally dilutes, this decay process could replenish dark energy, keeping their densities in a curious balance for a much longer period than pure chance would allow. It turns the cosmic coincidence from a bizarre accident into a predictable outcome of a connected system. but the interaction could be more direct and continuous, a concept known as coupled dark energy. Here, the dark energy field, whether it is a cosmological constant or quintessence, exerts a gentle force on dark matter particles, or vice versa. This coupling would act as an invisible transfer mechanism, a cosmic siphon moving energy from one reservoir to the other. The consequences would be written across the history of the universe. For instance, if dark matter is losing energy to dark energy, its gravitational grip on forming structures would weaken earlier than in the standard model. This would leave a distinct imprint on the number of giant galaxy clusters we see at different cosmic epochs. There might be fewer massive clusters today than our non-interacting models predict. It would also alter how sound waves propagated in the early plasma, subtly changing the pattern of the cosmic microwave background in ways that next-generation telescopes could detect. Perhaps most tantalizingly, such an interaction could offer a fresh path to resolving the Hubble tension. If dark energy was stronger in the past due to this coupling, or if dark matter behaved slightly differently, it would change the expansion history, bridging the early universe seen by Planck and the local universe measured by supernova. The two discordant measurements might snap into agreement if we account for this hidden conversation. Searching for this phantom dialogue requires the most subtle cosmological detective work. Astronomers are not looking for a flash in the dark, but for statistical whispers in large datasets. They run sophisticated computer simulations of the universe's evolution with different interaction strengths baked in. Then compare the virtual cosmos they create, the predicted distribution of galaxy clusters, the subtle lensing of voids, the precise clustering of galaxies against our actual maps of the sky. Any consistent mismatch could be the signal. It is a search for a ghostly handshake, an interaction that shapes everything from the largest structures to the fate of all existence, yet leaves its signature only in the grandest averages of the cosmos. If we find it, we will have discovered that the two greatest mysteries of the universe are, in fact, one. A new eye has opened in the endless dark, and it sees in the light of creation. The James Webb Space Telescope, stationed 1,000,000 miles from Earth, is not merely another observatory. It is a time machine engineered to witness the universe's first light and dissect its deepest shadows. Its primary power lies in its infrared vision. While our eyes and most telescopes see the universe as it is now, Webb sees the universe as it was, because the expansion of space has stretched the ancient, visible light from the first stars and galaxies into the infrared part of the spectrum. It can peer through cosmic dust and look back over 13 billion years to a period called the Cosmic Dawn. This is the epoch when the first galaxies were igniting inside their cocoons of dark matter. For the first time, we will not just infer the dark matter scaffold from simulations, we will watch it being built. Webb will capture those infant galaxies in the act of formation, showing us their shapes, their sizes, and their motions with unprecedented clarity. By studying how these primordial structures cluster together and how fast they spin, astronomers can perform a direct test of our models for cosmic structure formation. Do these first galaxies match the predictions of our cold dark matter simulations, or do they show the peculiar signatures of something else, like self-interacting dark matter or even primordial black holes? Webb's deep field images are not just pretty pictures, they are forensic scans of the cosmic crime scene, revealing how the invisible architect first laid its bricks. But Webb's mission extends beyond the first galaxies to the stellar explosions that light the way to dark energy. Remember, our knowledge of the accelerating universe rests on the dimming of distant Type Ia supernova. The farther back we look, the more crucial these measurements become for understanding if dark energy changes over time. Yet, observing these supernova at extreme distances has been plagued by a cosmic nuisance, dust. Interstellar dust in the host galaxies can redden and dim the supernova's light, mimicking the signal of accelerated expansion and introducing a major source of error. This is where Webb's infrared sight becomes a game changer. Infrared light passes through dust far more easily than visible light. By observing these ultra-distant supernovae primarily in the infrared, Webb will see them more clearly, measure their true brightness with far greater precision, and effectively subtract the confusing effects of dust. This will give us a cleaner, sharper record of the universe's expansion over the last 10 billion years. We will not just have a few data points, we will have a pristine curve, a detailed history of how the push of dark energy has evolved. Did it kick in suddenly, or has it been a gradual takeover? Does its strength show any sign of wavering, hinting at a dynamic quintessence field? Webb's data could provide the definitive answer, directly testing the cosmological constant against its rivals. This pristine data is also the key that could unlock the Hubble tension. The discrepancy between the local and early universe expansion rates is the most urgent crisis in cosmology. Webb addresses both sides of the rift. By delivering a supremely accurate measurement of the expansion rate from the distant supernova, it will either confirm the higher local value with unassailable precision or reveal a hidden systematic error in our previous measurements. Simultaneously, by peering back to the cosmic dawn and mapping the earliest structures, it will provide new, independent constraints on the physics of the early universe that feeds into the Planck CMB predictions. It is as if we have been listening to two orchestras playing the same symphony out of sync. Webb is not just turning up the volume, it is giving us the original score, note by note, allowing us to hear exactly where the discord begins. Whether it confirms our standard model or shatters it, the James Webb Space Telescope is not just observing the dark universe, it is interrogating it, demanding answers from the first light to the last. While the James Webb peers into the cosmic dawn, a different kind of eye is about to open on a Chilean mountaintop, one that will watch the entire sky in motion. The Vera C. Rubin Observatory is not a telescope that will stare at a single patch of darkness for weeks. Instead, it is a relentless cosmic surveyor, equipped with the largest digital camera ever built, containing over 3 billion pixels. Its mission is the Legacy Survey of Space and Time, a 10-year marathon of observation that will utterly transform our view of the dynamic, changing universe. Every few nights, its giant mirror will sweep across the entire southern sky, capturing an immense high-resolution portrait. Then it will do it again. And again, night after night for an entire decade. This will not produce a single, static map of the cosmos, but a colossal time-lapse movie of the heavens, revealing everything that moves, flickers, or explodes. The sheer scale of data is almost incomprehensible. The survey will catalog tens of billions of galaxies and track the positions of over 20 billion stars within our own Milky Way. But for the mysteries of the dark universe, this relentless watch is a game of statistical power. Imagine trying to understand the ocean by studying a single wave. Now imagine you have a satellite that films every wave on every coast every second for 10 years. Your understanding becomes definitive. The LSST will apply this principle to the cosmos. It will discover not dozens but millions of Type Ia supernova. Each one is a standard candle, a marker of cosmic distance and expansion. With millions of them spread across every epoch of the universe's recent history, we will no longer have a sketchy line describing dark energy's influence. We will have a densely plotted, ultra-precise curve. Any subtle wiggle in that curve, any indication that the repulsive push of dark energy grew stronger or weaker over the past few billion years, will stand out with crystal clarity. This could be the definitive evidence that dark energy is dynamic quintessence, not a static cosmological constant, but the survey's power goes far beyond supernova. By tracking the subtle, coherent distortions in the shapes of billions of distant galaxies, it will perform the most detailed weak gravitational lensing map ever conceived. This will let us see the dark matter web in higher resolution than ever before. tracing its distribution across the sky and through cosmic time with statistical certainty that washes away random noise. Simultaneously, by mapping the precise three-dimensional positions of galaxies, it will measure the Baryon acoustic oscillation standard ruler with such immense volume that the universe's expansion history will be pinned down with unprecedented accuracy. And it will catalog millions of galaxy clusters, weighing them through lensing and studying their growth, which is exquisitely sensitive to both dark matter and dark energy. This multi-pronged assault creates a powerful cross-check. If the supernova data, the lensing data, and the BO data all tell the same story about how dark energy behaves, the conclusion will be inescapable. But there is an even more radical possibility hidden in this ocean of data. The LSST might reveal that dark energy is not uniform. What if its strength is slightly different in one direction of the sky compared to another? Such an anisotropy would shatter our current models completely, suggesting a fundamental lopsidedness to the vacuum of space itself, or an imprint from something beyond our observable universe. The Vera C. Rubin Observatory's decade-long stare will give us the statistical muscle to ask these profound questions and demand answers from the dark. It will turn the mystery from a puzzle of a few clues into a problem of overwhelming evidence where the truth, however strange, can no longer hide. These cosmic surveys are the broad strokes, but the universe demands a finer brush. To truly map the geometry of the unseen, we need missions designed from inception for a single purpose: to interrogate the dark. The European Space Agency launched such a specialist in July of 2023. Named for the ancient Greek father of geometry, the Euclid Space Telescope carries a solemn duty to measure the shape of the dark universe itself. Euclid's strategy is twofold: a masterclass in cosmic triangulation. Its primary tool is weak gravitational lensing on a staggering scale. Euclid will image billions of galaxies across 1/3 of the sky, measuring their subtle, distorted shapes with a precision never before achieved from space. Each tiny distortion is a clue, a whisper of the dark matter that warped the light's path. But Euclid does not stop at a flat picture. By taking spectroscopic measurements of tens of millions of these galaxies, it will determine their distances, constructing a vast three-dimensional map. This allows scientists to see not just where the dark matter is, but how its distribution has evolved over cosmic time. The second pillar of Euclid's mission is to trace the imprint of Baryon acoustic oscillations, those frozen sound waves from the early universe. By mapping the positions of so many galaxies in 3 dimensions, Euclid will measure the scale of this standard ruler with exquisite accuracy at different epochs, charting the expansion history with a powerful, independent method. Together, these measurements will produce the most comprehensive dark matter map ever created, a cosmic CT scan revealing the skeleton of the universe in breathtaking detail. It will test whether dark matter truly behaves as a simple, cold, and collisionless fluid, or if its interactions leave a trace in the grand architecture. While Euclid charts the broad geometry, a different observatory will plunge into the deep. NASA's upcoming Nancy Grace Roman Space Telescope, named for the agency's first chief astronomer, is a powerhouse of pure discovery. With a field of view 100 times larger than the Hubble Space Telescopes, Roman is built for both wide and ultra-deep surveys. It will execute a core mission dedicated to uncovering the nature of dark energy through 3 simultaneous high-precision probes. First, it will discover thousands of the most distant Type Ia supernova ever seen, piercing through cosmic dust with its infrared eyes to build a flawless record of the universe's acceleration. Second, it will conduct its own weak lensing survey, rivaling ground-based efforts but without the blurring effect of Earth's atmosphere, to map dark matter with razor-sharp clarity. Third, it will perform immense galaxy redshift surveys to measure Baryon acoustic oscillations across an unprecedented volume of the cosmos. Roman's unique power lies in its ability to do all this at once with consistent space-based precision. It is not just looking for one signature of dark energy, it is building a consolidated case, cross-examining the cosmos with multiple, redundant lines of evidence. This multi-pronged approach is designed to eliminate systematic errors and deliver an unambiguous verdict. Together, Euclid and Roman form a historic partnership, a tag team of cosmic detectives. Their data will be complementary and synergistic. Euclid's wide geometric map provides the grand context, the continent-scale topography of the dark web. Roman's deep, multifaceted surveys provide the intense forensic detail, the close-up examination of how dark energy has behaved across billions of years. By combining their findings, cosmologists will construct a three-dimensional dark matter map of unparalleled scope and precision, a dynamic atlas of the invisible universe. This is not merely about making better maps, this is about putting our models through a trial they cannot escape. The combined data will have the statistical muscle to distinguish between a static cosmological constant and a rolling quintessence field with definitive confidence. It could reveal if dark energy has changed strength over time, or even if it varies subtly across different directions in space, a finding that would revolutionize cosmology overnight. These missions represent our most focused, deliberate step yet in the dark universe investigation. They are not general-purpose observatories hoping to glimpse the mystery. They are specialized instruments built to solve it, engineered to finally force the shadows to speak in a clear, measurable voice. Their launch pads are the starting line for a new era, one where we stop merely wondering about the dark and begin to chart its very laws. But the hunt for the phantom architect always returns to the particles that might be hiding in plain sight. Among the most elusive of all candidates is the sterile neutrino, a ghost within a ghost. We know that three types of neutrinos exist: electron, muon, and tau neutrinos, and they flood the cosmos, trillions passing through your body every second. Yet these are left-handed particles spinning in a specific orientation, and they interact via the weak nuclear force, however feebly. The sterile neutrino is their hypothetical right-handed mirror. It would spin the opposite way and, crucially, feel none of the fundamental forces except gravity. It would not interact via the weak force, the electromagnetic force, or the strong force. It is, by design, sterile. Its only connection to our world would be through an incredibly tiny mixing with its ordinary neutrino cousins, a quantum whisper that might allow it to oscillate or transform into a detectable form. This makes it a perfect dark matter candidate, massive enough to provide gravity, yet so aloof it could have evaded detection for decades. But why suspect such a phantom exists? The evidence comes from a series of stubborn, unresolved anomalies. For years, experiments studying nuclear reactors have measured fewer electron antineutrinos than predicted at short distances, a discrepancy known as the reactor antineutrino anomaly. One possible explanation is that some of these neutrinos are oscillating into sterile neutrinos that the detectors cannot see, vanishing into the dark sector. Even more tantalizing is a mysterious signal from the depths of space. X-ray telescopes observing the hot gas in galaxy clusters have repeatedly detected a faint, unexplained emission line at an energy of 3.5 kilo-electronvolts. No known atomic transition produces this specific energy. A leading hypothesis is that it comes from the decay of a sterile neutrino with a mass of about 7 kilo-electronvolts. In this scenario, a sterile neutrino in a galactic dark matter halo would very rarely decay into an ordinary neutrino and an X-ray photon of that precise energy. It is a ghostly fingerprint, a potential death rattle from the dark matter itself. The search for this ultimate ghost is a global endeavor conducted on two fronts. At particle accelerators like Fermilab, scientists create intense beams of neutrinos and fire them over long distances to underground detectors. The goal is to watch for a deficit or distortion in the expected oscillation pattern as the neutrinos travel, a signature that some have morphed into sterile states along the way. These experiments, with names like Mini-BUANI and the upcoming SBN program, are exquisitely sensitive to these quantum transformations. The other front uses nuclear reactors as natural neutrino factories. By placing ultra-sensitive detectors at different distances from a reactor core, physicists can map the neutrino flux with precision. Any sudden drop-off or anomaly in the number of neutrinos counted could signal oscillation into sterile modes. It is a painstaking process of accounting, looking for missing particles in a sea of quantum noise. The sterile neutrino embodies a profound possibility. That dark matter is not some exotic new entity from a hidden sector, but a member of our own particle family, a cosmic introvert that has simply turned its back on the world of light and force. Finding it would mean the answer was here all along, a ghostly sibling to the most abundant particles in the universe, silently holding everything together. The universe's first light was not a brilliant dawn, but a cold, silent fog. Before stars, before galaxies, the cosmos was filled with a simple, pristine gas, neutral hydrogen. And this hydrogen, even in the dark, hums a quiet, universal song. It emits a faint radio whisper at a very specific wavelength, 21 centimeters. This signal is the key to a time machine far more powerful than any telescope. In the darkness of the cosmic dawn, the first brilliant objects, perhaps massive stars or voracious black holes, finally ignited. Their intense ultraviolet light began to flood the universe, exciting the vast sea of hydrogen around them. As this light passed through the cooler, denser clumps of hydrogen gas strung along the filaments of the dark matter web, it was absorbed. Each clump at a different distance and moving at a different speed due to the universe's expansion, would absorb the light at a slightly shifted 21 centimeter wavelength. The result would not be a single line, but a complex spectrum of thousands, perhaps millions, of absorption lines. Astronomers call this the 21 centimeter forest. It is a barcode imprinted on the light of the first cosmic objects, and every single line in that barcode contains information. The spacing, the depth, and the width of these lines tell us about the temperature, the density, and the motion of the hydrogen gas at that precise moment in cosmic history, over 13 billion years ago. But here is where the dark matter connection becomes profound. That hydrogen did not clump randomly. It fell into the gravitational wells sculpted by the dark matter. The properties of the dark matter itself determine how fine or how coarse that cosmic web was at such an early time. If dark matter was cold and collisionless, as in our standard model, it would have formed a very specific, fine-grained web of filaments and tiny halos. This would produce a particular pattern in the 21 centimeter forest, a dense, intricate thicket of absorption lines. But if dark matter was different, the forest would change. What if dark matter was warm? This refers to hypothetical particles that were moving fast enough in the early universe to smooth out the smallest clumps. A warm dark matter universe would have a much coarser web with fewer, larger hydrogen clumps. The 21 centimeter forest would be sparse with fewer, broader absorption lines. Even more intriguingly, what if dark matter interacted with radiation? If dark matter particles could scatter off photons or even off themselves, they would transfer heat, warming up the hydrogen gas. Warmer gas is more energetic and resists collapsing into small clumps. This, too, would dramatically alter the fingerprint of the forest, erasing the finest lines and leaving a smoother, simpler spectrum. Detecting this ancient barcode is the monumental goal of a new generation of radio telescopes, most notably the Square Kilometre Array. When fully built across remote sites in South Africa and Australia, the SKA will not be a single dish, but a vast network of thousands of radio antennas working in concert. It will be the most sensitive radio ear ever pointed at the sky, designed to listen for the faintest cosmic whispers. Its primary mission is to tune into the 21-centimeter signal from the cosmic dawn to decode that primordial forest. This is not a simple task. The signal is incredibly faint, buried under a cacophony of radio noise from our own galaxy and Earth-based interference. Separating it will require years of observation and staggering computational power to process the data. But if the SKA succeeds, it will give us something we have never had before, a direct three-dimensional map of the universe's structure during its first few 100 million years. We will see the dark matter web not through its gravitational effects on later galaxies, but in the very gas it was sculpting at the time. It is a direct probe of dark matter's nature in its youth, long before the complications of stars and supernova muddied the waters. The 21-centimeter forest is more than a new observation. It is a conversation with the infant cosmos. By reading its lines, we are asking the universe a direct question about what shaped it, and the answer will be written in the language of the dark. This line of reasoning forces us to confront an unsettling possibility about our own existence. The cosmological constant's value is not just fine-tuned, it is absurdly, impossibly perfect. If it were even a hair stronger, the universe would have expanded so rapidly that no stars, planets, or people could ever have formed. If it were a hair weaker, gravity would have pulled everything back into a catastrophic big crunch long before life arose. The odds of landing on this razor's edge seem impossibly small, yet here we are. One controversial way to resolve this is to invoke a cosmic lottery with an infinite number of tickets. This is the multiverse hypothesis. In this view, our universe is just one bubble in a frothing, eternal sea of universes, each with its own random set of physical laws and constants. In most of these bubbles, the cosmological constant is enormous, ripping space apart instantly or zero, leading to a swift collapse. But in a vanishingly small fraction, by pure chance, the number lands in the narrow, habitable range. We, of course, can only find ourselves in one of those rare, life-permitting bubbles. Our existence is not evidence of a designed cosmos, but a statistical inevitability. We are the winners of a lottery we had to win in order to be here to ask the question. This is the anthropic principle in its starkest form. It finds a strange home in string theory, which mathematically predicts not one universe, but a staggering landscape of possible universes, perhaps 10 to the 500 different vacua, each a different stable configuration of dimensions and forces. In such a landscape, every possible value for the cosmological constant and every possible set of physical laws is realized somewhere. Our universe is not special, it is simply one address in an infinite cosmic metropolis. But does this truly solve the mystery, or does it merely relocate it to an inaccessible realm? For many scientists, the anthropic argument feels like a philosophical surrender. It replaces a testable physical explanation with a logical tautology. We see what we see because we are here to see it. It risks halting the scientific quest, suggesting that some of nature's deepest constants are not dictated by fundamental law, but are merely environmental accidents frozen into our local bubble. There is no experiment we can perform, no observation we can make to confirm or deny the existence of these other universes. They lie forever beyond our cosmic horizon. This moves the question from the domain of physics into the realm of metaphysics. Yet, its proponents argue it is the only honest answer to a genuine statistical miracle. The debate cuts to the very heart of what science is for. Are we searching for a single, elegant theory that uniquely predicts our universe, or are we cataloging our local bylaws in an infinite, chaotic cosmos where every possibility is realized? The mystery of the cosmological constant's perfection may not point to a deeper law of physics, but to the humbling limits of our own perspective, trapped as observers in a single, fragile, golden bubble. Perhaps the most unsettling question is also the simplest. Could we be completely wrong? For all its predictive power, the standard model of cosmology rests on two colossal assumptions: that we understand gravity perfectly on cosmic scales, and that we occupy a typical place in a broadly uniform universe. What if both are illusions? Some of the most radical theories in physics suggest that dark matter and dark energy are not substances at all, but mirages. They might be emergent phenomena, side effects of a deeper reality we have yet to comprehend, much like the pressure and temperature of a gas emerge from the chaotic dance of countless invisible atoms. One provocative idea is called entropic gravity, proposed by physicist Eric Verland. It suggests that gravity itself is not a fundamental force, but an entropic force, a consequence of the universe's natural tendency toward disorder. In this view, the apparent pull of gravity is what happens when the microscopic quantum information of space-time rearranges itself. The extra gravitational effects we attribute to dark matter could simply be how this emergent gravity behaves in regions of low acceleration, like the outskirts of galaxies. It is a complete reimagining of the cosmic order, where the phantom scaffolding is not made of particles but of information. Another mind-bending possibility concerns dark energy. What if the universe's accelerated expansion is not a property of space, but a trick of perspective? This is the giant void hypothesis. Our standard model assumes the universe is homogeneous, the same everywhere on large scales. But what if, by a staggering cosmic coincidence, our Milky Way galaxy resides near the center of an immense billion-light-year-wide void, a region of significantly below average density? If we were sitting in such a vast underdense bubble, the gravitational landscape would be lopsided. The relatively empty space around us would exert less gravitational pull, while the denser matter beyond the void's edge would create a gradient. From our lonely vantage point, it might look as if all distant galaxies are accelerating away from us, mimicking the effect of a repulsive dark energy. The redshift of their light would be interpreted as cosmic acceleration, when it might actually be due to this colossal density difference. It is a cosmic optical illusion on the grandest possible scale. These paradigm-shifting ideas face immense, some would say insurmountable, challenges. Entropic gravity, while elegant, struggles to explain the clean separation of mass from normal matter seen in the bullet cluster without invoking some form of unseen substance. The giant void hypothesis requires a void so vast and so perfectly centered on us that it violates the very cosmological principle it seeks to save, making our place in the cosmos not just special but absurdly privileged. Furthermore, detailed studies of the cosmic microwave background and the distribution of galaxies strongly support large-scale homogeneity. Yet, the value of these radical alternatives is not in their likely correctness but in their defiant spirit. They force us to confront the bedrock of our assumptions. Every great revolution in science, from realizing Earth orbits the Sun to understanding that space and time are relative, began by questioning something everyone believed was obviously true. Our current model, lambda CDM, is spectacularly successful, but its two central pillars remain utterly mysterious. To solve them, we must be willing to ask the heretical question: what if the clues are pointing us in the wrong direction entirely? The final mystery may not be out in the dark cosmos, but within the limits of our own imagination. Deep beneath the Black Hills of South Dakota, in a cavern once filled with gold miners, a new kind of prospector waits in absolute darkness. It is a cylinder of titanium 10 feet tall, containing 10 tons of liquid xenon kept at -100 degrees Celsius. This is Lux Zeppelin, or LZ, one of the most sensitive dark matter detectors ever conceived. Its mission is to listen for the universe's quietest sound, the gentle bump of a wimp against the nucleus of a xenon atom. The principle is deceptively simple, but its execution borders on the miraculous. If a dark matter particle enters this frigid tank and interacts, it will produce two signals: a quick flash of scintillation light and a delayed pulse of ionization electrons pulled upward by a powerful electric field. By precisely timing and locating these twin signals, scientists can pinpoint the exact three-dimensional location of the interaction and, crucially, distinguish a potential dark matter event from the relentless background noise of cosmic rays and natural radioactivity. LZ is not alone in this silent vigil. In an underground laboratory beneath the Gran Sasso mountain in Italy, its rival, Zeno NNT, holds 7.6 tons of liquid xenon in its own ultra-pure core. These experiments represent the vanguard of a direct, hands-on assault on the WIMP parameter space. They are scaling up in the most logical way more target mass. A larger volume of xenon means more atomic nuclei, which increases the statistical chance of that one in a quintillion interaction. Each new generation of these detectors is designed to be 10 times more sensitive than the last, probing deeper into the territory where shy dark matter particles might hide. But the ambition does not stop there. On the drawing boards is a concept called Darwin, a visionary detector that would scale up to 40, perhaps even 60, tons of liquid xenon. Darwin would be so exquisitely sensitive that it would not only search for WIMP, but also act as an observatory for other elusive phenomena, like the hypothesized neutrinoless double beta decay. It represents the ultimate expression of this technological path, a behemoth of purity and precision, waiting in a silence so profound it could hear the universe whisper its oldest secret. Yet the future of detection is not monolithic. As the xenon programs push the limits of scale, other brilliant minds are pursuing entirely different paths, betting that dark matter might leave a different kind of fingerprint. Imagine a detector not of liquid but of a quantum fluid. Projects like super cryogenic dark matter search use superfluid helium, cooled to a fraction of a degree above absolute zero. In this bizarre state, helium loses all viscosity and becomes a perfect quantum medium. If a dark matter particle strikes a helium nucleus, it creates a tiny wave of vibration and heat. In the superfluid, this interaction can generate both phonons, which are quantized sound waves, and rotons, which are quantum vortices. Exquisitely sensitive sensors lining the chamber can detect these minuscule excitations. The advantage here is twofold. Helium is a lighter nucleus than xenon, making it potentially more sensitive to lower mass dark matter particles, and its ultra-pure, simple atomic structure reduces background in unique ways. Another frontier is in solid crystals. Experiments like CREST and DAMIC use calcium tungstate or silicon crystals, respectively, cooled to cryogenic temperatures. When a particle interacts in these crystals, it produces both a tiny flash of light and a minuscule rise in temperature. By measuring this dual signal with superconducting sensors, they can achieve incredible sensitivity to very small energy deposits, again targeting dark matter candidates that are lighter and would be missed by the heavier xenon nuclei. Then there are the quantum amplifiers, devices that operate at the very edge of Heisenberg's uncertainty principle. By using quantum squeezing techniques, scientists can reduce the intrinsic noise of their sensors, effectively making the detector's ear more acute. This is not just about building bigger, it is about listening smarter, using the rules of quantum mechanics to silence the quantum noise of the detector itself and hear the signal beneath. This multi-pronged global effort is a testament to both our ingenuity and our profound uncertainty. We are building traps without knowing the shape of the ghost. Each experiment is a bet, a hypothesis cast in titanium and xenon, in helium and silicon. The field is balanced on a razor's edge of anticipation. The null result, the continued silence, is itself a powerful result. It relentlessly shrinks the territory where dark matter can hide, ruling out vast swaths of possible masses and interaction strengths. It forces theorists back to their chalkboards to imagine ever more exotic possibilities. But the other possibility, the one that electrifies every scientist in those deep underground labs, is a handful of events that cannot be explained by any known background. A few data points clustered in energy and position, a signal that rises and falls with the seasons, matching the Earth's journey through the galactic dark matter halo. That would be it. The moment the phantom touches the machine, the next generation of detectors is not just an incremental improvement, it is our best and perhaps final chance to catch dark matter in a regime where it must show itself if it is the wimp we long suspected. We are setting the most sensitive nets at the edge of the known, waiting for a ripple in the dark that will change everything. From the silent depths of underground labs to the sweeping gaze of space telescopes, this journey has mapped the contours of our ignorance. We have followed the gravitational shadow of dark matter from the spinning arms of galaxies to the wreckage of cosmic collisions, and traced the repulsive push of dark energy from the fading light of supernova to the swelling emptiness of cosmic voids. These 30 mysteries are not mere gaps in our knowledge. They are the very framework of modern cosmology, the pillars upon which our understanding of the universe is built. They tell us that the cosmos we perceive is a luminous decoration on a hidden architecture, a performance guided by unseen hands. The profound takeaway is that solving these puzzles will demand more than just better measurements. It will require a revolution in physics itself. The answers lie beyond our current standard model of particles and may even require us to rewrite Einstein's theory of general relativity. We are chasing phantoms that could redefine the fundamental forces of nature. Yet this is not a story of despair, but of breathtaking opportunity. You and I are living in a golden age of cosmic discovery. Within our lifetimes, the relentless data from observatories like Euclid, the Roman Space Telescope, and the Vera Rubin Observatory will converge. The silent chambers of LZ and Zeno NNT will either hear the whisper of a wimp or force us toward stranger possibilities. We are on the precipice of revelations that will reshape our place in the cosmos. So stay curious, look up at the night sky, and remember that most of what makes it exist is still a mystery waiting to be solved. Which of these 30 puzzles captivates you the most? Is it the rhythmic signal from the heart of a mountain, the phantom fingerprint in an X-ray line, or the terrifying possibility of a final big rip? Share your thoughts below, and if you want to join us for more deep dives into the universe's greatest secrets, be sure to subscribe. The greatest story ever told is still being written, and the next chapter is ours to discover.